Hello, I'm Louca, Softcat's Security Chief Technologist, and today we're going to be talking about network segmentation. Now, network segmentation might not be the first thing that comes to mind when you think about cybersecurity, but actually it's a very effective technique against isolating attacks within your environment. Today we're going to be looking at 3 different network models and seeing how they compare against each other. The first model we're going to be looking at today is the single trust boundary. Now, the single trust boundary only, as the name implies, has one layer of trust. And this is the model we're looking at. This is going to be very similar to most of our environments that we work in today. And actually, that control boundary is placed by a number of firewalls. Those firewalls control the access from outside of the trust boundary to inside the trust boundary. In this model, we're going to assume that we work in an environment with 9 virtual machines. This just helps keep the numbers nice and small, but you'll be able to see actually how the math scales. So we have a web, app, and DB tier. Okay? And these 3 applications are your sole control and responsibility. We're going to look at the reachability of each of these services via a number of different threat actors. And the reason we're doing this is because this gives us an empirical way of testing the different security models. One of the key challenges we've found over the years when looking at cybersecurity approaches for organizations is that they're constantly chasing the threat. They're constantly looking to find a product that fixes an issue. And one of the key challenges with that is that you're constantly investing. You have to keep reinvesting to defend against the latest threat. Now, one of the great things about network segmentation is ultimately it relies on a very simple principle. If you can't reach the server, you can't hack it. So what we're going to be doing today as part of this modeling is we're going to be testing that reachability. We're going to be doing our tests from 3 different locations. The first is an external threat actor. So this would be someone that is external to your organization, so i.e. someone on the internet or potentially somebody outside of the organization. Now, this external threat actor that we draw on here, they're going to have to pass through this single trust boundary. So if we imagine this being an internet-based user, on average, most organizations only have about 20% of their services exposed. So we're going to see this external threat actor pass through this security layer and is going to be able to access one of these 2 systems. So we had the single trust model, and that was an external threat actor. And as I said, we could reach 2 of the virtual machines, which is about 22%. Now, 22% is probably a totally acceptable risk amount. At the end of the day, every organization has to accept some risk. That's the cost of doing business. So actually, 22% is probably fine. You're never going to get that number to 0. But now let's take the second scenario. Previously, we had our external threat actor out here. Let's think about if that threat actor migrated to within the trust boundary. We'd call that an internal threat actor. Now, this scenario is actually more common than I think most people account for. Typically, the way the threat actor will migrate is they will compromise an internal computer, deliver a piece of malware to a machine via email or potentially a web link that would be run by a member of staff, and that external threat actor would suddenly have an internal placehold in the network. Now, if we now look at this threat actor can now reach all 9 of the servers. That migration from this external position through the trust boundary and inside the organization has increased that risk score for that organization from 22% to 100%. That reachability is massively increased. So we can see immediately some of the disadvantages of that single trust boundary. As the name implies, there is one layer of security, and if you breach that layer of security, you will lose all protection against that threat actor. So now if we take our third and final scenario, an internally compromised server, this threat actor is now sitting on one of these virtual machines. So in this model, we have exactly the same amount of reachability, 100%. We have the server threat actor. Okay, so what you can see here in summary, the single trust boundary is the traditional, most common way of providing network security and segmentation at the moment, but actually only stands up to an external threat actor. As we can see from our numbers, 22% for external, but 100% for internal and server. As soon as that threat actor migrates within that boundary, the whole system falls down. Now let's look at the second model. This is the dual trust boundary. So similarly to the first model, it has the same exterior boundary, but in addition, it has an internal layer. So let's draw this up again. So we've got our external trust boundary. As with the other model, you have your firewalls from the outside. They're the controlling access from outside the environment. And you've got your same 9 virtual machines. Let's just draw these in right now. Now, the difference between this model and the first model we discussed is this additional internal layer. So this internal layer sits between the campus networking and the external layer. And these can be protected by either firewalls or ADCs. So now ADCs are the posh name for load balancers. And I particularly like using them for protecting this internal layer. They have a number of really useful security characteristics that we can take advantage of. Now, firstly, ADCs, when deployed in line, are what's known as a default deny device. And what that means is that they won't pass traffic that's not set up on them. And that's really, really useful, and we'll kind of explain why a little bit later. The second characteristic that's really useful is they're what's known as a full TCP proxy. Now, what a full TCP proxy is essentially what happens now is that when you communicate to the server, rather than communicating directly from your client straight to the server, you pass it through the ADC, and it repeats that message on your behalf. It's a little bit like Chinese whispers. Now, let's test this with our first scenario, the external threat actor. So, as with the first model, you've now got an external threat actor, somebody from outside the environment. And again, they've got to pass through the first security boundary, as per the first model, and again, second into the internal security boundary. Now, nothing has actually changed between the first model and the second model in this scenario. Actually, both of the 2 virtual machines that were available previously are still available. So actually, this model scores no differently than the first model when we write it down on our table here. So we've got the dual trust model here, external threat actor, and 22%. Now, let's see how this model stands up when that threat actor migrates to the internal position. So the threat actor is now sitting on the internal environment. Differently from the first model, you now have an internal security layer that you must pass through to get access to those internal services. So in this scenario, we're now taking advantage of these ADCs and these internal security layers in this scenario. So what we've done here is, because we've got these web tiers, app tiers, and DB tiers, now only one of those layers needs to be accessible to those internal users so they can access their services. So what we're going to do is we would present those services through these ADCs. They would pass those traffics for those 3 virtual machines. But as I mentioned, these are default deny devices. These app and DB tier layers aren't set up and don't need to be. So actually what we've done is we've now hidden 2/3 of the machines from that internal threat actor. So as we migrate through here, we can see we can reach all 3 of these, but we can't get any further. Now, so we can now only reach 3 out of the 9 servers, 1/3. So if we mark that down in our table here, so we've got 33%. So as you can see, this is a really large reduction from the single trust model that was straight up to 100% as soon as we had that internally compromised client. It's now down to 33%. You know, a really, really useful reduction, and it keeps it much closer in line with that external threat actor. So now let's take the final scenario, the internally compromised server. So if we now imagine that we've got our threat actor sitting on this internal compromised server, and actually, let's see how far this internal actor can reach. So what's the network availability for those guys? So as you can see, there's no security boundaries between these different virtual machines. So as soon as that user manages to compromise that server, they have full accessibility again across the whole environment. So that takes us back up to 100%, very similarly to the single trust model. So we've got 100% here. So now what we can kind of tell from this is that the dual trust model is definitely an improvement against the single trust model. You know, we definitely start to build up better defenses against an internally compromised client, which is something that's becoming more and more prevalent in organizations. What we've seen over the last 12 months is that most organizations will suffer some level of internal breach. And actually, without this level of network segmentation, this could make a lateral movement incredibly easy for a threat actor. So now let's look at the third and final model. This is the zero trust model. So this model is Softcat's recommended approach to network segmentation. And this model differs from the other 3 in which it has not only the external layers, as per the first one, with its firewalls protecting the outside, and as per the previous model, we have this internal layer. It's here with our firewalls protecting that internal layer there. This model is almost the same, except for one unique piece. We now have segmentation within that internal security zone. And this is a services-based segmentation or a microservice architecture. And this has a number of really useful security characteristics, which will become apparent when we go through our different scenarios. But really what we're starting to build out here is a control between each of the virtual machines themselves. So if we see here, we've got our web app and DB tier. This makes one application. Well, the web app only needs to access one other server, the app server. And actually the app server only needs to access the database. So what we've done here is we've created a bubble around this service that puts additional security layers between the different virtual machines. So let's start our testing. So here's our external threat actor again. Again, passes through as per the second and first model. The external layer comes through the external layer into the second layer, hits the ADCs, which only present the web services that are set up on them, and we access those two external servers. So exactly as all the other models, we have 22%. So let's just draw these lines out here a little bit. And here we go. We've got our zero trust model, and we've got 22% here. So as you can see, we've kept the same all the way through. That external threat actor has had the same network accessibility in the single trust model, the dual trust model, and the zero trust model. Now let's look at the internal threat actor scenario. So the internal threat actor, as before, sits on the network. And as we described, that's becoming a more and more common scenario. So now we have our internal threat actor. And as we described before, that's becoming more and more common, with more and more internally compromised clients becoming prevalent within our networks. So let's run the same scenario. So how many servers can this internal client access? Well, as we mentioned before, you're going to pass through the internal security layer, hit onto the ADCs, and as I mentioned, the ADCs are default deny devices, so they're only going to pass services that are set up on them. So these three-tier applications, only the web tier needs to be accessible to actually function. So the ADC is only going to pass traffic to those top three servers. So exactly as the same as the dual trust model, we can reach 33% in our zero trust model. Now, let's see how the model stands up against an internally compromised server. So our threat actor is now sitting on that web server. And let's see kind of what's different about this model. So compared to the dual trust model, you can see that we've now got these internal layers of trust boundaries, and we can now control the access from each of those virtual machines. So as I mentioned earlier, the web tier only needs to access the application tier. So that's the only place the internally compromised threat actor can go. So they can now only access one further virtual machine. So if we put that back in our table, so 1 of 9 is 11%. So we can see a massive threat reduction by comparison to both our single trust model and our dual trust model. That zero trust model has been able to essentially build an environment that resists all attacks, no matter where they're located. And this is why we think this is the best way that organizations can go about defending their infrastructure. So let's come up for a summary. Let's look at the average network reachability across the three models. Firstly, the single trust model. As we saw, performed fairly well against the external threat actor, but not so well against the internal and server threat actor. That gave us an overall average of 75% reachability across the model. Now, the dual trust model performed better with the internal threat actor, bringing that second score down, but still failed on the server threat actor, giving us an average of 50%. And then finally, the zero trust model really shined. Its ability to defend against all the three different types of threat actors gave it a really low average score of only 20% network reachability. What I really like about the zero trust model is its consistency. As we saw, it was 22% for the external threat actor, 33% for the internal, and 11% for the server. That tight grouping of network accessibility is great for an organization because it allows you to understand the typical likely network accessibility for each of the different scenarios. You're not going to be surprised unlike some of the other models. Now let's look at a summary of what we should take away from these models this morning. So number one, you should model the network accessibility paths. You need to understand how your users access their applications. It's only by going through this will you understand which security boundaries you have in place and how they might potentially help you. The second one is isolate. By isolating and putting up security boundaries, you're reducing the risk of a major compromise. You're able to understand your risk from compromise from different threat actors to different applications in a much more confined way. And that keeps your risk level much lower. And number three is alert. One of the great things about implementing more security boundaries is each security boundary acts as an alert mechanism. So if you do have an incident, you've got a much more effective way or more sensors out there in the network to tell you when something's going wrong. Interestingly, this is very, very useful as part of preparation for GDPR. We all know we now have a 72-hour breach notification requirement. So being able to get those alerts, that high quality information, is going to make your ability to deal with that much, much easier. Thank you for watching the video. I hope it's been a useful introduction to network segmentation. And if you're interested in finding out how you can take this from architecture to architecture, get in contact with your Softcat account manager.